Greetings everyone, my name is Carlos Mota, and along with Didipia Baningala and Bindu Neelam of Team of 3, we are CS graduate students, and this is our final project for our Advanced Algorithms class. Our project title is Optimizing K-Means Clustering for Customer Analytics, a multifaceted approach. So basically what we're trying to do is take the K-Means clustering algorithm and provide several enhancements to a data set. Now, just based off that, the 4 different algorithmic enhancements that we're doing is parallel processing, where the goal there is if we have a very large data set, we can use several multi-threaded techniques to increase the processing power. The second approach is penalty scoring. So within K-means itself, the overall goal is to group data into specific clusters, and we measure the intervariance between how far it is to the actual mean of the data. So penalty scoring involves the farther a data set is away from the mean, the more penalty score it gets. The third iteration is the Manhattan distance. Typically, K-means clustering uses Euclidean distance, and for this estimation we decided to look at Manhattan distance, which is the absolute value distance. And for the final approach, we decided to add a probability element using Gaussian Mixture Models to assign the probability, or in other words, to throw in a percentage of chance to see how membership to a certain cluster is. So overall, the research questions that we're looking at is how do these enhancements generally improve accuracy and efficiency in terms of how we can group certain customers, their personality traits, their purchasing behaviors, things like that. And the other key research question is which combination of enhancements yields the most effective clustering. So if we go to this middle section here, we can see the naive approach, which is pretty much a greedy approach, is an unsupervised learning technique where a lot of it depends on the data set itself. So just going through the algorithm, we initially have to pre-process and determine how many initial centroids that we want to go with. Aside from there, the next step is pretty much assign the data to a certain average, and then from there this just continues repeating until there is a certain convergence check, and that pretty much ends the algorithm. In terms of our methodology, we can look at this right here, and pretty much it deals with a lot of the pre-processing, cleaning the data, introducing any new variables that we want to look at, any data processing techniques that we want to look at. For categorical, typically a lot of the data needs to be cleaned beforehand. These are the techniques that we employ, and we assign the data to a specific method, and then we provide evaluation metrics to see the overall results of how far a data set is to the average. So aside from that, our initial results were that the traditional K-means outperformed most of the other enhancements, but you can't look at it from a linear approach, because the parallel K-means would work better for larger data sets. So in reality, there is no perfect algorithm for any specific data set. That's where fine-tuning and other things come into play. For our comparison summary, here's just a summary of all the results that we got. And some of the trade-offs we have to analyze before we can come to ultimate conclusions. But these are just some of the conclusions we came up with. Traditional K-means itself performed best in terms of cluster separation. Traditional K-means also performed highest in terms of the Colentis-Harabaz index comparison. And what that does, it just calculates the within variance of the actual cluster. A lot of the improvements, there's a lot of caveats that we have to add to this. So in terms of fine-tuning specific parameters, but if you fine-tune too much, then you're kind of overcompensating. Here's just a summary of our conclusions, and this graph pretty much shows just a small segment of what the data would look like. It's all color-coded, so you can kind of see where the clusters are on the graph. In terms of the implementation, a lot of this was done in Python. We can see all the libraries that we use: pandas, clean the data set, make a classification, seaboard, and graphics. All this runs through a sampling of the data as well as putting it into data frames. Down here, here's a better picture of the scatter plot. We can see all the purples within the clusters. Now, if you notice with the data itself, one of the primary issues was the percentage of outliers that we had. So we addressed that problem using penalty scoring, which we'll see in a little bit. So here we are applying the actual k-means algorithm, and this is the results that we got. So overall, the Colinski score for the traditional k-means performed the best. For the parallel execution, for this we use the parallel processing for the delay functions. And aside from that, this is honestly the best for larger data sets. And we can pretty much see similar results. Now, in terms of penalty scoring, well, for Manhattan distance, this one just takes the absolute value of how far a data point is from the cluster average. And we can kind of see the results here, which are pretty similar as well. Now, for the probability element, we use a matrix to pretty much determine the probability of a certain cluster being within a node being within a certain cluster. And here we go, similar results. Okay, so overall, the project itself was very intriguing. The overall goal was to see if businesses or organizations can use this to ultimately find ways to better price their products. If the churn rate for customers depends on certain variables, companies can use that information to ultimately gain an economic gain on their end. So that pretty much concludes the presentation. Thank you for listening, and we appreciate it.